Hey everyone, and welcome to The Explainer. I am absolutely pumped to have you here today because we're tackling something that is literally foundational to computer science, but honestly, it's kind of misunderstood. We're talking about sequential data structures. Specifically, we're going to demystify queues and figure out how to properly optimize them in Python. You know, whether you've been coding for years or you're just brushing up, getting a grip on these hidden mechanics of memory management is an absolute game changer for how you write code.
So here's our quick roadmap for today. 1. The linear queue problem. 2. The circular queue solution. 3. The absolute magic of modulo arithmetic. 4. NQ and DQ logic. And finally 5. Python lists versus the built-in DQ. Okay, let's dive right into this. Section 1. The linear queue problem.
All right, so at its core, a queue is a linear data structure governed by a super strict rule, first in, first out, or FIFO. Think about it just like waiting in line at a coffee shop, right? The first person to step in line is the first person to get their coffee and get out. Now, this is the exact opposite of a stack, which operates on a last in, first out, or LIFO principle, kind of like a stack of plates. But in programming, queues are everywhere. We use them for handling printer jobs, scheduling tasks, managing web requests, the whole shebang.
But here's the catch. The traditional linear array implementation of a queue runs into a massive, frankly annoying problem. Let's think about it. When we insert elements at the rear, we use a rear pointer. When we remove an element, we take it from the front, so we advance our front pointer. Over time, as we're adding and removing items, both of these pointers just keep marching forward toward the end of our fixed-size array, and eventually, boom, that rear pointer hits the maximum size of the array. Now, here's the fatal flaw. Even if we've already removed a bunch of elements from the front, leaving these perfectly good empty spaces behind, those spaces are now completely inaccessible. The pointers have basically drifted to the end, and that vacated front space becomes permanently wasted garbage memory. We literally cannot store any more data, even though the array isn't technically full. It's so frustrating.
Which brings us to Section 2, the circular queue solution. So engineers had to fix this, and the solution is what's known as a circular queue, or you might hear it called a ring buffer. It's essentially an extended version of a standard linear queue, but with one incredibly clever architectural fix. The last position conceptually connects directly back to the first position, forming a continuous circle. By creating this circular link, we completely resolve that memory wastage problem. When our rear pointer hits the end of the array, instead of crashing or throwing a nasty overflow error, it just wraps right around to the beginning. That way we can reuse those empty spaces we freed up earlier.
And this brilliantly illustrates exactly what we're talking about. Imagine we have an array with a size of 5. The rear pointer is currently at index 4, so the very end of our physical array space. But notice, the front pointer is at index 1, which means index 0 is currently sitting there completely empty. Instead of being stuck, our circular incrementation logic smoothly wraps that rear pointer right back around to index 0. We're safely reusing memory and completely eliminating that garbage space problem we saw earlier. It's a real game changer.
So how does it actually wrap around? That's Section 3, the magic of modulo arithmetic.
The secret sauce behind all of this is the modulo operator, represented in code by the percent sign. Now, if you're a little rusty on your math, modulo simply returns the remainder of a division operation. So 5 modulo 2 equals 1, right? Because 2 goes into 5 twice with a remainder of 1. But here is the real magic trick. What happens when the left number is smaller than the right number? Like, what is 2 modulo 5? Well, 5 goes into 2 0 times with a remainder of 2, so it just returns the left number. In the context of a circular queue, the modulo operator acts as this perfect mathematical boundary wrapper. It naturally resets our pointers to 0 the exact moment they exceed our maximum array size. It literally creates infinite circular functionality within a rigidly linear memory space. Pretty cool, right?
Now let's see this in action. Section 4, NQ and DQ logic.
First up, the NQ operation, which is just a fancy word for adding data. Any robust NQ function is going to first check if the queue is full, to prevent an overflow error. If we actually have space, we insert our new element at the current rear index. Then we execute our circular incrementation. So rear equals rear plus 1 modulo the max size. Think about our previous example. If our rear was 4 and our max size was 5, well, 4 plus 1 is 5, and 5 modulo 5 is 0. Boom! The pointer wraps cleanly back to the beginning of the array. And the DQ operation perfectly mirrors this logic. When we want to remove data, first we verify the queue isn't completely empty. Got to prevent that underflow error. If we're good to go, we retrieve the data sitting at the front index.
And to effectively delete that element, we just advance the front pointer using the exact same circular incrementation. Front equals front plus 1 modulo max size. The beauty here is we don't even need to physically erase the data. By simply moving the front pointer, we've logically deleted it and opened up that exact space for the rear pointer to eventually overwrite.
All right, let's bring this into the real world. Section 5, Python lists versus built-in Deque. So knowing all this underlying math, the pointer management, the circular incrementation, you might be wondering, should you actually sit down and build a circular queue from scratch using a standard Python list? The answer to that is a resounding no, and here's why. A standard Python list is internally implemented as a C array. If you try to use a normal Python list as a queue and call pop 0 to remove the first element, Python literally has to physically shift every single subsequent element down one slot in memory to fill that gap. It's a massive performance trap. It creates an O of n operation that will absolutely crush your application's speed as the list grows. On the other hand, Python provides a built-in library called collections.deque, which stands for double-ended queue. This thing is C-based, completely thread-safe, and specifically architected for highly efficient appends and pops from both ends.
So the crucial point is that the official Python documentation actually warns us about this directly. It states, the list objects support similar operations, they are optimized for fast, fixed-length operations, and incur O of n memory movement costs for pop 0. Basically, building your own queue using standard Python lists is like reinventing the wheel, but making the wheel square.
By using a proper circular array implementation, or in Python's case, just utilizing collections.deque, we achieve the absolute holy grail of data structures. We get that sweet O of 1 constant time complexity across the board. In-queue, deque, peak, best case, average case, and worst case. No memory shifting, no garbage wasted space, just pure, uninterrupted performance for sure.
Which leaves us with this final thought. If something as seemingly simple as a queue can become a massive performance bottleneck when implemented incorrectly with standard lists, and if collections.deque perfectly abstracts all this math into safe O of 1 operations, well, what other foundational data structures are secretly slowing down your code base right now? It's always worth looking under the hood, isn't it? Thank you so much for joining me on this explainer. Keep learning, keep auditing your code, and we'll catch you in the next one.